I have a very, very easy job to do today. First, I want to thank the organizers for asking me to be here. But the easy job is to convince you of the incredible importance of speciation to conservation efforts, in particular to the efforts to avert a mass extinction, something we are all worried about. All of us who study speciation are fascinated with life's diversity and would be extremely upset were we even to predict that it had to disappear largely. I can hardly avoid beginning with a quotation from this pamphlet, which we all got today, and I was delighted to see it. And the quotation is right in the middle on page 7. It has to do with the biodiversity crisis. And it says that the role of speciation in the balance is generally ignored in biodiversity conservation efforts. Why? Based on the assumption that speciation rates are always too slow to contribute substantially. Well, what we have learned here today, and we will, I think, continue to learn, is that's not true. They're not too slow. And what one of my great teachers taught me a long time ago is that whenever you hear someone make an excuse, there's the good reason and the real reason. And in this case, the good reason was, well, it's just too slow to matter. The real reason, I think, is different. I think the real reason is that ecologists don't like to think about evolution. And they don't know very much about it. And we have to change that. And we are changing that. I'm very proud of what I heard here today and anticipate hearing much, much more like it in the next couple of days. Not only is it not too slow to matter, but I didn't put this microphone on. I wouldn't have needed it. But surprise, we are losing common species too, and speciation matters in that story. Surprise, a major effect of global warming on the diversity of life is to accelerate extinction, and the environment can't respond just because of the slowness of speciation. And that turns the argument, the good reason, right around on its head. Just because speciation is slow, it's important. I really have to say that the topic of this talk, therefore, or rather the conclusion of this talk, is that to prevent a mass extinction of species, conservation ecology must understand and appreciate the role of speciation. Okay. Why can I get away with saying that? How are we going to convince people who are ecologists who don't want to hear this that they better start listening if they care about diversity, and they do just as much as we do? Well, in the first place, I have to return to pattern. We've talked a lot about process today, but I'm glad to hear that people are talking about process to supplement what we know about pattern. There's still much to learn from pattern, and I will show you a little bit about that just now. This is one of ecology's most famous patterns. It is the pattern of the species-area relationship. It was invented by von Humboldt in 1805, and it has been studied ever since. It's one of the things that we know the most about, and it's been called ecology's law. We can express these relationships in a power equation, a very famous power equation, which we owe to Arrhenius. around 1919, and today we know that this equation is not exact, but it's a pretty good description. We have better models of the processes and the patterns that tell us that this is a pretty good description of what's really going on, and we can use it because it's handy. And I'm going to do that today, although it's not exact. I'm going to do it, however, at a scale which the conservation biologists rarely take into consideration, and that is the scale of the entire globe, bioprovince by bioprovince. When we do that, we see unusual values for the logarithmic slope, which is actually the curvature of the species area relationship. This particular work on freshwater fish shows the freshwater tropical fish of various continental areas in the world, each of which is a bioprovince. And you can see that the slope is not the kind of slope we're used to, 0.25, 0.30, 0.20. It is instead a slope very close to 0.9, and other situations return slopes that are similarly high, and we understand theoretically also why they should be much higher than the typical slopes that we see. But let me show you two more. This one actually comes from the tropical wet forests of the world, and each one of these is a bioprovince. These are vertebrate frugivores, bats, birds, and primates, and these are angiosperms, and in this case the slope is 0.97. In this case it is 1.15. The exact details are not important, and obviously there aren't enough points to talk about this as being significantly different from the freshwater fish one that I just showed you. Here's another one that comes straight from the fossil record from the work of Nicholas and Tiffany, and it shows the number of species of fossil trees known from the entire northern hemisphere. The northern hemisphere, because that's where most of the paleobiologists live, have sufficient data so that we can make this graph. This is not a graph of time, it is a graph that records the rising and falling of the ocean levels through 400 million years of time. And each of these periods that have been looked at are like a separate biogeographical province. There is endemicity within them, and we can see that they follow along a species area relationship which is so close to 1.0 that it returns 1.0 even in a multiple linear regression study, and therefore I've simply plotted it as an arithmetic plot to emphasize that there is no curvature in this particular relationship at all. Now these very steep slopes are in fact very special in the set of species area relationships, and this is a conceptual rendition of what we actually see in data. We see very, very steep interprovincial species area relationships. When we take one whole province and we look at pieces of them, we see the relatively shallow slopes, which in fact were first observed in the early 1800s and straight through until about 1990, when there was enough data to focus on provinces. And when we look at islands, we see slightly steeper slopes. But when we look at conservation biology, we see international conventions that declare on the basis of island biogeography what conservation should be doing to protect diversity. We see numbers like the Rio number of 20%. If you can, in fact, they say, protect 20% of the land, then you will be able to save most of its species. Where does that number come from? It comes from assuming island biogeography rules. It comes from looking at maps of reserves, such as this one from China, in which you see the land that's been reserved as a kind of measles epidemic across the face of the map of China. And if you think that that scale is inappropriate, here's a slightly smaller one from a slightly smaller country. This is England and Wales. And you again see, this is, I don't know what to call this disease, but you see this archipelago of reservations. The conservation biologist takes a look at that and says, island biogeography. Let's go and study this and work on it as if it's island biogeography. But in fact, the dynamics of island biogeography depend not on speciation, they depend on immigration. And if you look at the mathematics of them, you will see that there is an implicit assumption. And the assumption is, never does a species become extinct. Never. There is this big daddy pool of species on the mainland from which an island can always replenish its supply of an extinct species. That's fine in space, but it doesn't work in time until someone can show me how to resurrect the extinct species that went extinct 500 years ago and replenish it to the world of the future. I can't use the mathematics of island biogeography. I have to replace them with a different source of origination, and one in which global extinction is possible. And I did that a long time ago, but it looks very, very different. Not in its extinction curve, but in its speciation curve, which now has, over all or most of the number of species, a negative second derivative as well as a positive first derivative, whereas the island model has a negative second, a positive second derivative and a negative first derivative. It's exactly the opposite. And the results are very different too. Basically though, it does depend on the geographical model of speciation, a vicariant speciation. I'll have more to say about that yet. That doesn't mean to say that what I'm going to say has nothing to, is to deny the importance of the kinds of processes that we're talking about here, but it does mean to say that so far we know of a negative feedback signal that comes from area and that can influence that only from the process of vicariance speciation. And so if we're looking for the auto control of the system and understanding why it is what it is, we've got to have a variable like that, and that variable is the area, and the process through which it works is vicariance, biogeography, and we get a system which regulates itself by having new species enter and old species leaving. Fine. How does that affect province size? And the answer is very simple. Larger provinces should have higher curves of speciation and lower curves of extinction so that their steady states are displaced from left to right. That's what we're after, and that's what we'd like to know about. But we cannot ignore the great change in the climate of the Earth that we are forcing right now. And I'm not here to argue about how important it is at all. But I do want to combine a climate model with an area model and show you how nicely that works. We can do that today because of the work of the World Wildlife Foundation and their data set, which was made available to me, both the climatic data set and the number of species in the different eco-regions of the world, which allowed us to build a picture of what these things looked like at the bioprovincial level. They're the bioprovinces that we used, we experimented with others, and it turned out that for the most part Wallace was right all along. He had these identified for vertebrates. There are a couple we've been able to add, which is Hawaii. Madagascar is a different biogeographical province, and so is New Zealand. We wind up with 9 biogeographical provinces for the vertebrates, 50,000 species, land vertebrates. We wind up with those provinces, and that wasn't very pleasing to me. I don't like to work with only 9 points. And so I was kind of shocked to get the result that I'm about to show you. And that result is that if we look for area alone, we get already a highly significant correlation. Don't ask me for the equation, you won't want to see it in a second anyhow. And then if we look for the climate signal, we get nothing. Now that's wrong, but if we look at the residuals off of this relationship, and we use as a climate signal the actual evapotranspiration for technical reasons, that's often meant to do productivity, or we could look at the climate signal of simply annual average temperature. Doesn't matter which one you use, they're statistically almost identical in their effect on the variance, on the residuals around this curve. Here's the one for the residuals of actual evapotranspiration. It's pretty good, and I don't even want to talk about the size of the probability. It's about minus 10 to the minus 12. And when you put the two together, and now I'll show you an equation, you get that equation for the number of species in a bioprovince, the number of land vertebrates. It is equal to this power times the log area. This is a power, it's a logarithmic slope, it's that same number we've been talking about, and this is the effect of the climate right here. We don't have a process for that yet. We need one very badly. The R squared is nothing to write home about, it's only 97.3%. And I thought, wow, that's ridiculous. 9 points, 2 variables, 97.3%? So just so that I could see it with my own eyes, I made this transform variable out of this equation right here, and I graphed it. And it looks like this. It's remarkable. It tells the story, at least for land vertebrates. And it also tells us what we need to do to put an ecologist's telescope together that ought to begin to influence the conservationist. It tells us that we can draw a kind of topographic map which will in fact predict how many species will remain if so much and so much area is lost. How many species will remain because we depress the speciation rate? How many will we lose because we enhance the extinction rate? We do that together. And the forecast looks something like this. It's awful. Those Greek letters are just various ecologists' prognostications about how much energy we are taking from the world and how much land we have already taken from the world. And there is nothing here that is less than a mass extinction. The best we do is to keep about 35% of the world's species. 35%, the best. And I don't think there's anything very much to support this prognostication. Now we get a very, very interesting question for the speciation student. Maybe this variable, which is energy flow, isn't the right variable. Maybe some other variable, like the temperature, is the right variable. I mentioned that we get about the same pattern. We don't know what the process is through which speciation and extinction influence this particular pattern. If it's temperature, however, we must read off the top of the graph because we're not decreasing the temperature. In fact, we may be increasing it. And under those circumstances, we get slightly less of a mass extinction. Slightly less of a mass extinction. That's important, however, because we can't give the energy back, and if the problem is that taking energy out of the system is either increasing extinction or depressing speciation, we're in trouble. We're going to lose those species. But if the problem is more that raising the temperature is at the root cause, then we're not in so much trouble, because we can in fact work on the land surface area in a program that I've been calling Reconciliation Ecology, which means designing the systems that we use so that they also can be used by wild things. Not held prisoner only in nature parks and reserves anymore. I'm not suggesting we destroy those nature reserves, not at all. We need them too. And we could talk about that for an hour or two. I've never ever been to a place where one person or another doesn't give me a new example of reconciliation ecology. I encourage you, if you know them, just don't be upset by it, don't be ashamed by it. It's the wave of the future, it's what we need to do, and we already need to know it. And we have evidence, in fact, that this is the case. Let's look, for example, at the extinction rates, which we can document very nicely on mountaintops and on the Sunda Islands. These are of mammals. And you can see that the larger the area, the lower the extinction rate. We get in the fossil data from Dave Jablonski the same precise kind of conclusion. Here we have the percentage of extinct species rising through time. And for small-range species, these are bivalves and gastropods along the eastern shore of the United States and then down around Florida in the Gulf of Mexico. And these are fossil deposits in the late Cretaceous. And we get this very, very steep rate of extinction for the small range species. The large range species, on the other hand, just bumble along and become extinct fairly slowly. We know also from the fossil record that we can expect the existence of these steady states. This is the work of Blair Van Valkenburg, for example, and she's shown that North American large mammals over the course of 45 million years have maintained roughly a steady state of diversity. They have not increased. These things have to be corrected for sample size bias in order to see the true signal, and I've done that also in the Nicolet River Valley in Quebec. I've done that for the data that the Bretskys took out of the late Ordovician, which was a very, very exciting time for life. The muddy benthos was in fact invaded at that time. It's a new period, and we see, notice this, a very strong signal of a high rate of speciation over here, and then everything bumbles along. And you can actually see on top of the steady state, you can actually extract the speciation rates, and they look like that. The speciation rate at the beginning, and then a pretty sharp decline toward a plateau, which is never reached because there's a mass extinction at the end of the Ordovician. As I heard some of the talks today, and in particular, I had a discussion with Skule about this at the last coffee break, it seemed to me that some of the processes we're talking about, like the speciation that comes from ecological pressure, may be active only in new systems like this one, or in systems that have suffered mass extinction. They may be characteristic of systems that have not achieved any kind of a steady state yet. And once we get to steady state, there is now accumulating evidence that those things become less and less important as processes, and the more traditional vicariance speciation takes over. But there's a problem here. We can do pretty well measuring extinction rates in the fossil record, but we're having a lot of trouble measuring speciation rates in the fossil record. There's been some progress, and I admit to a little bit of it myself. This particular equation is a deterministic equation that we published, that Sarah Vito and I published in 1992, and it separates the rates of extinction from the rates of speciation. Because what you see in the fossil record are accumulations. They're called diversification rates in the literature, and that's a good term. It's good to separate the two. And what we were able to do was show how mathematically one could do that. Recently, Etienne and Apol, in a paper in 2009, checked this on the same data that we worked on, which was the African data on the extinction rates of various antelope families. And they found that it was working. And more important, they developed a stochastic method, which is a real tour de force in measuring speciation rates. It replaces the deterministic statement of how much the speciation rate is with a probabilistic statement about that. And so you have a probability distribution around the number of species that are extinct, the number of species that are alive, and the amount of time that goes on. And that's just too long an equation for me to write down on this slide. But I encourage you to go to the Pages of Evolution in 2009 and look up this paper. It's bound to become a classic. It's already been applied by Smith et al. In the Pages of Evolutionary Ecology Research to the case of 65 million years of evolution of the fishes, the freshwater fishes of North America. That's a huge data set. And the answers that they get are amazing, but I'm troubled by them. There's a dissonance here. The answers they get over the 65 million year period are that the speciation rate of freshwater fishes is perhaps close to an order of magnitude less than the speciation rate of antelopes in Africa. I don't believe that. Fishes really speciate fast. We've seen that again and again. What's going on? I don't know. We need to improve this technique, and much more important, we need to develop it to the point where we can do the sorts of things that we can already do for extinction rate. That is, we can track the speciation rate through time, over evolutionary time, with some confidence that we've corrected for biases in the sampling. I think that's what's going on in the analysis that Smith et al. Produced. There's, in the 65 million years, the scale at which they're looking is so vast, and the amount of biases, sampling biases, that they are subject to are so great that they are not seeing most of the speciation events which actually have occurred. So it's a great advance, but it points to a need that we have for the future of speciation research. We're getting close to dinner, and I'm not going to go on more. I could. I've got a 5-hour battery life in this computer. But I'm just going to finish by the place that I started, which is to say that if we are going to prevent a mass extinction of species, we have to convince the conservation world that it must understand and appreciate the role of speciation. Thanks.
Yeah, thank you, Michael. Do you have any questions?
You. Yeah.
Okay, thank you for an excellent talk. Of course, this is really a very big challenge to us to run this on a political level as well. But I have a question. Quite many of the species in any ecosystem are extremely rare. I've actually myself done a small one survey and found out that surprisingly it seemed to be that about 30 to 40% of all the species are so rare, so the taxonomists call them singletons. That means that they only find them in one individual among all the hundreds of thousands of individuals they are gathered. I don't know what's wrong with this microphone.
but I can hear you, and I'll repeat your question.
Okay. So my question is really, when we talk about these extinctions, is it the rare species, or is it more or less a random over kinds of species? I mean, also the very common ones, or is it the rare ones in the first place?
The question, to repeat the question briefly, is if you look at a collection of species, most of them are rare. 30–40% was the estimate, are singletons. Is that right? And so what's becoming extinct here? The rare species or the common species or some mixture of them? The answer is it's a mixture. We are very surprised, not me, but conservation biologists were very surprised 2 years ago to see the results of an Audubon survey that showed that something like 30–40% of the very common birds in North America had plummeted in population over a couple of decades. You would also be surprised, if you thought they had to be rare, to note the massive extinctions of some species. The world's most common bird in the year 1800 was the North American passenger pigeon. It had a population of 4 billion. It was almost extinct. Nobody knew it. The American chestnut, which I think will make a comeback because of some good genetic work, the American chestnut covered 25% of appropriate forests in Canada and northeastern US. And it's virtually extinct now. Because of one disease. Another instance was a case of a littoral snail that fed on eelgrass. It was immensely common in New England until about 1930, when a viral disease came across the ocean and attacked its food supply. But it attacked the food supply only in the salinities required by the snail. And so the snail is utterly extinct. We find the extinction of common species in the record again and again and again and again. And we should stop fooling ourselves that only rare species become extinct. I think the whole red list is fine for a start. But it fools us to think we don't have to worry about the world's common species. What this says is 90 to 99% of the species on the face of the earth are marked for extinction. We can't tell which ones. Trying to tell which ones is like trying to identify the molecules of water that will boil away when you make coffee in the morning.
Another question down there first.
Thank you very much.
Now, if yours is not working, I need you to speak because I can't hear all that well.
I think it's a very important encouragement that we make here about our role in communicating with the conservation of the ecosystem. Just, I would like to just give one more phrase it in a simple way. What is the first thing we need to do?
What is the first thing who should do? We should do? The conservation biologists should do? Again, say the
How should we approach them?
I guess with candy and flowers. That's always a good way. Persistence, a smile, and the knowledge that they care as much about diversity as we do. And my approach to them has been to encourage more and more reconciliation and to encourage them to take pride in what they're doing, because they're doing the right thing. They may not appreciate it, they don't appreciate yet why. But once they're doing the right thing, then they'll be more open to understanding why it's the right thing. There's an old, in fact it's Talmudic axiom that says if somebody's doing something, for some ulterior motive, it's still good, because eventually out of the ulterior motive he'll do it for the right reason.
I take one final quick question from Isabel.
I just want, I wonder how to actually implement an agenda in speciation that would be applied. And my feeling is that if we want to promote, I agree with you, the speciation is low, but I think natural selection is pretty rapid, at least in some organisms. And maybe we could promote that the idea of having natural selection being implemented. And the only way I can see, I mean, the easiest way would be to promote the idea that we need to have reserves which are as heterogeneous as possible. Because, I mean, like, this is one mechanism that we know is promoting diversification is by heterogeneous.
That's absolutely correct. That we do need to promote heterogeneity, and we also need to promote that heterogeneity in these reconciled landscapes that I'm talking about. That's a hard sell. Most of the time, people look at a landscape and they say, it looks green to me. And they ignore the heterogeneity. We're also finding out in our own research that patchiness, that fragmentation, plays a much smaller role than we thought it did. That we don't have to be quite so afraid of fragmentation as we thought we did. And we can talk about that. But it will come because these are the kinds of things that non-professionals can do in their own neighborhoods. And we're experimenting with that in Tucson, and other people are elsewhere too.
But aren't ecologists already convinced of this? I mean, do we actually need to convince them?
Yeah, we need to convince them. Trust me. I've been working on this since 1997, and I've heard it all. I mean, we're out of time, right? I'll tell you some of the funny things I've heard, but afterward.
We can continue the discussion over the dinner later.
Yeah.